Hello everyone, and welcome to our first lesson of our next unit, Unit 3, which is exponential functions. So we're going to start off with saying, well, what is it? What does it look like? What's the equation like? And kind of just doing some experimenting with it so you guys can have a chance to play around and get comfortable with this new equation. You've probably seen it before, maybe in Unit 1 we maybe looked at it, but we didn't really analyze it or graph it in any sort of detail. So we're going to start off with what our equation looks like in the most basic form, which is going to be f of x equals b to the power of x. So noticing how it's called exponential functions, which means it has to have some kind of exponent, right? Exponent, your variable now is in the exponent, which is something different. And here we have b, which is just your base, and that number can change. We can have 2 to the power of x, we can have 3 to the power of x, we can have negative a half to the power of x, right? That base is going to be something that changes. But as you know in our course that we focus a lot in Unit 1 about transformations, and that does not go away. So if we want to take this and say, well, what does this look like if I add all these transformations onto it? We get f of x equals, don't forget that we have an a value, which says our vertical stretches and compressions. That base still stays there, right? That base is something that changes, depends on what your function is. K comes up here in the exponent in front of our x minus d, right? So our k is that horizontal stretch or compression. It also can flip across the y-axis. Our d value is a horizontal shift. And at the end, we can also have a plus c value. So that's great and all that you have an equation, but what does this look like? So we're going to take a look at Desmos. And I encourage you to open up Desmos on your own computer so that you can play around with this yourself. I'm just going to help us set it up. So we're going to say here, instead of f of x, we're going to have y equals a. Let's pick, for now, we'll pick our base to be 2 so that we can just play around with the transformations. So I'm going to put here 2 to the power of x as our base function that we can compare it to. So now we can have a look and see, well, what does an exponential function look like? It takes this shape, which can change with transformations, but that's our most basic shape. And you can see how it's a very slow growth here off to the left side, but as it goes to the right, as our x values get bigger, there's huge jumps in that growth. So now we're going to play around with this and say y equals, we need to add some letters in here, so our a value, we'll keep our base as 2, so we have something to compare it to. No, 2. Two to the power of, we need our k value up there, k bracket x minus d, and then plus c. Awesome. So once you have this, then you can add your sliders, and that's something that I would like you to do so that you can play around with it, right? So if we have everything as equal to 1, that's what it looks like, but we can change our k value and see what happens if we make k really large, and see what happens if we make k more like a decimal. And what if k goes into the negatives? We have a flip, a complete flip. Same with c value. You can play with what happens here, noticing what happens if it goes negative or positive. You can put it back as close to 1 as you can and go change your d value and also play with the a value and see what happens. So that's kind of what I'm hoping for, but now we have a general idea of what they look like. I'm going to take that off for a second. So here, when we have just 2 to the power of x, we have an example of what's called exponential growth. As x values get larger, then our y values get really, really large, right? It's getting bigger every time. But what if we flipped it around? And again, with your sliders, you can play around with this. what if I had y equals 1/2 to the power of x? So notice how this blue graph is the exact flipped version, and it's basically doing the opposite. When our x values get bigger from 10 to 20 to 30, our values are actually getting smaller, smaller and smaller and smaller, and they're getting closer and closer to 0. So going back here, we want to talk about, well, how do we know if we have an example of growth? Well, usually with just a basic graph, you can tell visually, but right away we can see that our base would have to be greater than 1. Anything bigger than 1. 1.5, 10, 100, any of those things are going to have a base, or a base greater than 1, which shows as growth. But what about decay? So again, after you've played around, you can probably make this conclusion on your own, something that we would have gotten you to do if we were here in person. But if you pick your base to be a fraction, so something anywhere between 0 and 1, that's also going to give you decay, just in that original form of just the base to the power of x. You can also pick growth and decay from, like, pick it out through transformations. So growth is always going to look like, if that's my little axis, then it looks like this, right? It is growing. It's getting bigger as x gets bigger. And our decay is always going to look like this. So whether you do that with transformations or whether you have that with your base as greater than 1 or between 0 and 1, that's kind of the shape that you are looking for with your growth and decay. So my question for you now is going to be, what if your base is 0? What if your base is equal to 1? Because notice how above I have b is between 0 and 1, not greater than or equal to or less than or equal to, right? It's greater than, less than. So what if it actually is equal to 0 or equal to 1? What happens? Do you still have an exponential function? You can pause and play on Desmos and find out. But really we're going to find out that they're not exponentials. They just end up being straight lines. Straight horizontal lines. Not exponential. Okay, so I also want to talk about how can we see that in another way, like prove that it's exponential. How is it different from a straight line, a quadratic, a cubic, any other kind of function? So let's again take the function f of x is equal to 2 to the power of x. It's a good place to start, but there's obviously lots of other bases around there and lots more transformations. So if we make a table of values, let's do, I don't know, -1, 0, 1, 2, 3, let's go up to 4. So if we take those x values and plug them in, so 2 to the power of -1, we get 1/2 or 0.5. If we plug in 2 to the power of 0, remember that 0 rule, anything to the power of 0 is 1. 2 to the power of 1 is 2. 2 to the power of 2 is 4. And we have 8 and 16. So if we do our first differences, like you would way back when, going back to grade 9, you would take your first differences. I would say, okay, the difference here is 0.5. The difference here is 1. The difference here is 2. 4, 8. They're not the same. So we know for sure it's definitely not linear. We know that visually, but now we're kind of just proving that. Okay, what if I take my second differences? Okay, we do the same thing. We get 0.5, 1, 2, and 4. Again, they're not even the same. They're not even getting any different. They're all the same. So what are we noticing here? Maybe you started to see already that these are actually connected through multiplication. So that's a different thing. Before we were doing the differences like subtraction. Here, it's not going to work that way in exponential. Everything is growing or decaying through a factor, through multiplication. So that's kind of the difference here with exponential functions, is that everything is connected through multiplication. So the last thing I want to talk about in this little intro to exponential functions is domain and range. So we'll start with a nice simple one where we have f of x equals 2 to the power of x. So we really have to bring that back from our first unit. So when we're thinking about our domain, we want to look at all the x values going from left to right. What values are allowed? Is there anything that's not allowed? Even though it looks like right over here that it kind of like stops here, it doesn't. It's going to keep growing forever and ever and ever and kind of move towards that right side. So we're going to say that x is every real number. And that works because no matter how big the number is, you can still plug it in to x over here. There's nothing that would not work. You would just get humongous. Now for our range, we kind of want to see what numbers can be produced, right? Is there anything that can't be produced based on this graph at first? So by looking at the graph, we can see that everything above the x-axis, perfect. Everything below the x-axis, there is nothing. So we would say like every number in between above the x-axis is possible. So we're going to say y is a real number. But, right, remember that vertical line telling us but, y actually has to be greater than 0. Not greater than or equal to, because it will never equal 0. You can see here it's getting closer and closer and closer to 0. But if you zoom in on Desmos, you'll see it's never ever going to touch. That's a horizontal asymptote, which means the line gets closer and closer and closer to it every time, but it will never touch. So that's going to be our domain for an exponential, a basic exponential graph. So now your job is to do the domain and range of this function and then check your answer based on the graph. So I want you to try f of x is equal to negative 3 to the power of negative x plus 4 minus 8. You can think about the transformations and then go from there, or you can plug it in on Desmos at first as you're getting comfortable with it. Use Desmos to graph it first and then base your domain and range off of that. Maybe I'll post the solutions in our weekly document. All right, see you later.